In this video, we're going to be diving a little bit deeper into redox reactions and how we can tell whether or not a particular reaction is a redox reaction, because it's not always obvious. In the example we looked at in the last lesson, it was pretty obvious because we were just dealing with monatomic ions. Their charges were changing, therefore they must be gaining or losing electrons in order to be either losing their charge and becoming neutral or gaining a charge as a cation. But it's not always that obvious. So in a lot of cases, we need what are known as oxidation numbers in order to figure out whether oxidation and reduction are happening in a given process. So oxidation numbers are just a sort of method for quantifying the extent of oxidation of an atom. We'll say of an atom in a particular compound, because the same element can have different oxidation numbers in different compounds, as we're going to see. So the reason why oxidation numbers are useful is that for more complex reactions, it can often be difficult to determine whether or not redox is happening. Just from the charge. Often there is no change in charge when there is in fact redox happening. So what we need to do is assign oxidation numbers, and we'll talk about how to do that in just a second. And if you see that the oxidation number for an element changes between the reactant side and the product side, redox is occurring. Its oxidation state, the extent to which it is oxidized, has changed. So that means if your oxidation numbers changed, you have a redox reaction on your hand. Specifically, increasing oxidation number means that that element has been oxidized. And a decrease in the oxidation number means that that element has been reduced. So you should always find, if you are dealing with a redox reaction, that something's oxidation number increases and something else's oxidation number decreases. You should always find one going in either direction, because we know that oxidation and reduction always occur together. So how we assign oxidation numbers is governed by a set of rules that take the form of a hierarchy. So the first thing takes precedence over the second thing takes precedence over the third thing, so on and so forth. Because not only do certain elements have preferences for what oxidation state they prefer to be in when they can, some of them have stronger preferences than others. So some elements have a very strong preference for exactly the oxidation state they want. Others are a little bit more agreeable and tend to have various different oxidation states in different compounds. You'll notice that we don't have rules for every element on the periodic table, but we do have rules for a lot of the groups that we commonly encounter. So you'll see a lot of them are governed by the family that the element is in, and you will notice that those ones governed by families are the same as their preferred charges. So group 1A when they form ions, like to have a +1 charge. They also like to have an oxidation state of a +1. Group 2A, same deal. That's the second column from the left. Those like to have +2 charges in ionic compounds. They also like to have an oxidation state of +2 where they can. But the one thing that takes precedence over everything else is this one, that the sum of all oxidation numbers for all atoms in a molecular ion must be equal to the charge on the species. So that is always, always, always going to be true with no exceptions ever under any circumstances. So, for instance, if we want to assign oxidation numbers to all atoms in each of the following things, and we're going to do a few so that we can see some different types of situations. First things first, let's say we do F2. First thing to keep in mind is when you are assigning oxidation numbers, you are assigning them to each individual atom of that element. And for the purposes of this course, we are going to assume that all elements within, all atoms of a given element will have the same oxidation number in the same compound. So in this example, we have 2 atoms of fluorine connected together. We are going to assume that each of those 2 atoms has the same oxidation number, and that is going to be true for the examples I give you. So if we look through our list of rules, we see that there is a preference for fluorine, and fluorine prefers to have an oxidation number of -1, but that doesn't matter because rule 1 exists, and because rule 1 is more important, that the sum of all of our oxidation numbers must equal the charge. The charge on this thing is 0. There's nothing shown as a superscript here, so the charge is 0, which means that the oxidation number here for fluorine is 0, regardless of its preference. Preference doesn't matter here. The sum of our oxidation numbers has to be 0, and we only have one element, therefore its oxidation number is 0. To look at another example, CH4. So let's look at what would the oxidation number for carbon be, what would the oxidation number for hydrogen be. So looking through our list of rules, we don't find a rule for carbon. It doesn't have a preference. Carbon is very flexible. It can have lots of different oxidation numbers, but we do find a rule for hydrogen. So we see that hydrogen prefers to have an oxidation number of +1 when bonded to a nonmetal or metalloid, which is the common one, -1 when bonded to a metal, which almost never happens. We have the hydrogen bonded to the carbon here, which is a nonmetal. So we know that that hydrogen is going to have an oxidation number of +1. It gets its preference. So essentially, whichever ones you assign first get their preference. You go in order of the list. So we don't have any fluorine, we can skip rule 2. We don't have any 1A or 2A elements, we can skip rule 3. We get to rule 4, hydrogen, this is relevant to this compound. So because hydrogen is highest up on our list, that is going to get a +1. And what we have to keep in mind is that this has a +1 oxidation number, and there are 4 of them. Each atom has a +1 oxidation number times 4, and then carbon doesn't have a rule, so all we have to do is make sure that rule 1 is satisfied. So if we have 4 hydrogen atoms, each with a +1 oxidation state, that means that in this compound, the carbon must have an oxidation state of -4. Let's look at one more. Let's do 2 more. We have CH2F2. We have now, order, go, there we go. Carbon, hydrogen, and fluorine. Looking down our list, the first thing we encounter is fluorine. So we have fluorine in our compound. It is going to have a preferred oxidation state of -1. It is going to get its way. Continuing down our list, we don't have anything that applies to rule 3. Rule 4, we do once again have hydrogen. It is once again connected to a nonmetal, so that is going to get its preferred oxidation state of +1. That once again leaves us with carbon as kind of our question mark here, where we don't have a rule that applies to carbon, so it's just going to get whatever oxidation state it needs in order to satisfy rule 1, to make sure that the sum of all of our oxidation numbers is once again equal to 0, since the charge on our species is 0 here. So we now have fluorine with an oxidation number of -1, and there are 2 of those. We have hydrogen with a +1 oxidation state, and there are 2 of those. So our sum is already at 0, which means we don't want to change it. So this carbon is going to have an oxidation number of 0, and that is a valid thing that can and does happen and is correct here. So our hydrogens and our fluorines already added to 0, means carbon must also be 0 in order for our overall total to be 0. And last but not least, let's look at one where the hierarchy aspect of this really starts to matter, because things will not always get their preferred oxidation state. So let me erase some extraneous stuff here. We have potassium, which is a group 1A metal and prefers to have an oxidation state of +1, apologies. And then we have oxygen, which prefers an oxidation state of -2. Now, if both of these things were true, our oxidation numbers would not add up to our charge. If we had 2 potassiums, each with a +1, and 2 oxygens, each with a -2, we would have a grand total of -2 overall. And we can see there's no charge here, so these oxidation numbers must add up to 0, which means that one of these elements is not going to get its preference, and that is okay. This is where this idea of a hierarchy comes into play, and that whichever element is higher up on your list gets assigned first and takes precedence over anything that is further down. So in this case, that means that the potassium is higher up on the list. It is going to get that +1 oxidation state. The oxygen, being further down, is going to have to just fall into line in order to satisfy rule 1. So rule 1 is more important than anything else. So if we have 2 potassium ions, each with an oxidation number of +1, and we have 2 oxygen atoms, they must each have an oxidation number of -1, which is not oxygen's preference, but that's okay, and that's what it has to be in this compound in order for it to work, in order for the sum of our oxidation numbers to equal the charge. So once we get the hang of assigning oxidation numbers, how we actually use them is to determine whether or not oxidation reduction is happening. So we're going to look at an example where I will tell you up front that oxidation and reduction is happening, and we're going to determine what is being oxidized and what is being reduced. And we can do that also using oxidation numbers. So if we have iron reacting with HCl to form iron 3 chloride and hydrogen gas. So to determine what's being oxidized and what's being reduced, also note the reaction isn't balanced. It doesn't need to be. It doesn't matter. You can balance it for practice if you would like to. To determine what is being oxidized and what is being reduced, we need to look at our oxidation numbers. So going through our list here, for iron, it is just 1 atom by itself with 0 charge. So in order for our oxidation numbers to add to 0, the one and only oxidation number must be 0. In the next one, we consult our list. We find that hydrogen is higher up than chlorine, which is going to be filed under group 7A here. Oops, that was supposed to be an eraser, sorry. So we'll assign hydrogen first with its preferred oxidation number of +1, which means that the chlorine must be -1. As it happens, that is its preference. You will often find that everybody gets their preference, but not always, so it is sometimes important to get that hierarchy in the correct order. On the product side, there is no rule for iron, which means we get to assign chlorine first. And each of those chlorines is going to be -1, and there are 3 of them, which means in order for the total charge to be 0, the iron must have an oxidation number of +3. And then last but not least, we only have one element in this molecule with a total charge of 0, so the oxidation number must be 0. So we have 3 different elements involved in this process. We have the iron, which is going from an oxidation number of 0 to +3. We have the hydrogen, which is going from +1 to 0. And then we have the chlorine, which is staying at -1 the whole time. So the chlorine was neither oxidized nor reduced, since its oxidation number stayed the same. But we do see that we have this oxidation number increasing, and we have this oxidation number decreasing. So we have, as we talked about earlier, one going in each direction means one thing was oxidized and one thing was reduced. So specifically, this change of iron 0 to iron 3+ is an oxidation, is losing electrons. Our iron is becoming more positively charged, so it must have lost those negatively charged particles. And the hydrogen is going from +1 to 0, so it gained some electrons and is being reduced. So in this reaction, we would say iron is oxidized and hydrogen, or HCl, however you care to phrase it, you can either talk about the specific element or the molecule as a whole. So the iron is oxidized and the hydrogen is reduced, and we can tell that by how the oxidation numbers change. If you look at a reaction after assigning oxidation numbers and you find that for every single element there is no change, that means it wasn't an oxidation reduction reaction. So we can tell both what is being oxidized and what is being reduced by looking at how the oxidation numbers change, as well as just, is this a redox reaction at all, for whether or not the oxidation numbers change. So if there's no change, there's no redox. If there is a change, it is redox, and we can tell the thing that is oxidized has its oxidation number increased, and the thing that is reduced has its oxidation number reduced or decreased.